We're looking at vector projections or vector resolutes, and this is a useful skill, and what we're looking at is with a given vector A and a given vector B, we're looking at resolving. So we're going to resolve A into W and U, and A is given and B are given vectors. So A and B exist first up. We're going to resolve them into W and U. Now it is also given that U is parallel to B and W is perpendicular to B. So given that we have U is parallel to B, we can say that U equals some scalar multiple of B, or KB, where K is a scalar. I'm going to call that result 1. We can also say that, looking at the diagram, A equals U plus W, head to tail. Alright, A equals U plus W. We'll call that result 2. W, therefore, is A take U, or A plus negative U. We'll call that 3. And we also know that from 1 above, so from result 1 above, W would also equal A take KB. Alright, because we can place U of KB. Now, since W is perpendicular to B, that means W dot B equals 0 from what we know about the dot product. So we can replace using from 3. We can say, instead of W here, we can say A minus KB dotted with B equals 0. So just combining these two lines up with result 3 as well. So expanding that out, then we have, using our past properties of scalar product, B dot B still equals 0. So we have, rearranging that, we have A dot B equals K outside of B dot B. So rearranging again, K would equal A dot B divided by B dot B. Now we can do that because these are scalars, so they're real numbers or scalars. While vector division is not defined, scalar division certainly is. We know that the two dot products yield scalars, so that's fine to divide that. So from 1, and remember 1 was up here, U equals KB. So from 1 we can say that U equals KB written like that, u equals kb. Alright, so k, remember, k is replaced by that. Now we have our result, and this is basically saying that u is the vector projection of A in the direction of B. Okay. U is the vector projection or the vector resolute of A in the direction of B. So written formally, there it is. Okay, the vector resolute of A in the direction of B can be expressed in these forms here. So that's what the equivalent to what we just saw above there. And what they're doing is manipulating it. So B dot B is the magnitude of B squared, as we've learnt previously. Okay, and then manipulating it further, we eventually get this form here. Note that this form is called the sine length of the vector resolute u and is called the scalar resolute in the direction of B. Let's look at a simple example in this video. There'll be later videos which expand this idea a bit further. So let A equals I plus 3j and B equals I minus j. Find the vector resolute of A in the direction of B. So we go in and we do that then. So that would be A dot B over B dot B times vector B. Okay, it's just like an adaptation of what we saw up there. You could call it vector u if you like. And we can do that now. So let's see. So let's see what we've got. So A dot B, let's work that out first. So A dot B is 1 times 1 plus 3 times negative 1, which is negative 3, which is negative 2. So A dot B is negative 2, and B dot B is 1 times 1 plus negative 1 times negative 1, which is 2. So we would have plugging it in then, that would mean that we've got negative 2 over 2 times vector B, which was I minus j, and that's negative 1 outside of I minus j, which could be written as negative I plus j, or even j minus I. Let's look at the next one. B in the direction of A. It's just showing the adaptability I should say, of the formula. So we basically interpret the formula using what we've got to find, and it would be B dot A over A dot A times vector A. Okay, so because of commutativity, B dot A is going to be the same as that there, and so we have negative 2 on the top. A dot A would be 1 by 1, so it would be 1 by 1, which is 1, plus 3 by 3, which is 9, which is 10. So that would be 10, and vector A is I plus 3j. So it's negative 1/5 I plus 3j